Yeah, welcome everyone to the Tom class. In the today's session, we are going to start a new topic, which is dynamic analysis. It's a very small topic. We have already studied mechanisms and machines, velocity and acceleration analysis. In this chapter, um, or in this small topic, our aim is to understand the dynamic analysis of the link, where we will focus on mainly, let's say, if a sliding pair is there or a turning pair is there, how what are the forces which we can see, and if we take example of, let's say, slider crank chain, what are the how the force system will look like, and the last point which we'll be studying in this topic is dynamically equivalent link. Okay, so this is the overall idea about this chapter, and after this we will start the balancing chapter. Okay, balancing of reciprocating and rotary masses. So with this introduction, let's start this chapter. I'll go to the next slide. Write down heading sliding pair. Okay, we know sliding pair means we have a piston, and piston is connected to the or piston is sliding on a surface, which you can say a guideways. Okay, what so it is not in equilibrium, it's moving now. So what force you can expect here? What is the summation of the force here? Net force on the axis of reciprocation, what you can expect? Can you tell me? This is, let's say, the axis of reciprocation. Okay, so it is reciprocating like this. So if I ask you what is the net force along the axis of reciprocation, what should be the answer in this case? We know it's mass m, and it is moving with some acceleration a. So the net force, I would say, summation f will be equal to mass times the acceleration. Okay, it's very simple when we focus it on a sliding pair. But if we talk about the turning pair, not that easy. Sean, yeah, I think you have answered it for mr omega square. Why it is mr omega square? It's not a rotating pair. Okay, it's not a rotating pair, so omega will not be there. So mass time acceleration, friction I am not considering here. Okay, it's without friction, that's why just mass times acceleration we are using. But friction is always there if mass is moving in one direction, and if coefficient of friction is there in between surface and the body, then frictional force will be in the opposite direction. Okay, but mainly in theory of machines topic, our we make our assumption simpler, that without friction most of the time we do the analysis, and that's why I'm just writing here ma. Okay, what about the turning pair? Can you tell me what are the different forces or moments you can expect in a turning pair? So here I have shown a turning pair. Let's say the center of rotation is O, and let's suppose we have one point here which is CG of this. Okay, this is center of gravity. Okay, so I can assume that, or let's say I can say that it is same as like this turning rod. Okay, okay, with let's say at CG we have mass times acceleration due to gravity is mg load is acting downwards. Is it correct? And the CG is at the distance r from the center of rotation. So can you tell me, uh, apart from mg, what you can expect here? Like if will it create moment, that this mg force about the center of rotation, will it create some moment? Okay. So for example, you are applying some torque. Okay, let's suppose you are applying some torque in order to move. Let's say tau is the torque. You are applying this torque mm, in order to move this, or in order to turn this um, uh, what you can say, um, a pair in the counterclockwise direction. Okay, so what moments I can expect here is moment about O would be tau minus mg times r cos of alpha. Let's say suppose this is or theta. Let's assume this as theta. Then let's say this is bar is moving with um, omega rpm, and alpha is and angular acceleration. Okay, these are the assumptions. So with these assumptions, what we can say is tau is equal, sorry, total moment about origin will be tau minus mg r cos of theta, and that will be equal to the, that will be equal to what? That will be equal to the inertia moment. Okay, so that you can say as I naught alpha. Correct. So in general, the total torque, you can say it as I naught alpha I naught alpha plus mg times r cos of theta, where tau is the torque and alpha is, you can say, theta double dot. Okay, theta is the angular displacement, theta dot is angular velocity, and theta double dot is angular acceleration, which is alpha. So this is how you can expect the um, equation of the moment in case of turning pair. Okay, so now let's take a complicated system, like where we have both turning pair as well as sliding pair. Okay, so that is nothing but a slider crank mechanism. So write down heading dynamic analysis of the slider crank mechanism. So in this case, how many turning pairs are there? How many turning pairs are there? Yeah, no, we have 3 turning pairs. We have 3 turning pairs and we have 1 sliding pair. It's a single slider mechanism. Why? Because in between link number 1 and link number 2, you have a turning pair. In between link 2 and 3, we have a turning pair. In between 3 and 4, you have a turning pair. And in 3 and 1, you have sliding pair. We have studied this, right? In the first chapter itself, that in a single slider crank chain, we have 3 turning pair and a sliding pair. So a simplified version of it I have drawn below. You can have a look. That let's say R is the length of the crank, L is the length of the connecting rod, and at particular moment, let's say the crank is making an theta degree angle with respect to the horizontal, or the along the line of reciprocation, and connecting rod is making the angle phi. Okay, and let's say if um, this is rotating it with some omega, for example. Okay, then what I can expect is the slider will will be having some translatory motion along the axis, and it will have some velocity vn, acceleration alpha, for example, or acceleration a. Why a? Because it's a linear acceleration, you should denote it by a. So v and a is the linear velocity and linear acceleration of the sliding pair. Okay, omega is a um, rotating speed of the crank. Okay, is it clear till this? Now let's try to understand the force system. Okay, before understanding the force system, what is the s value here? If you tell me what is the total distance at this particular moment, you should be able to calculate. You know the r, you know the l, so you should know the s. It is x, sorry, it is r times cos of theta plus l time cos of phi. Is it correct? Sorry, yes, r cos of theta plus, can I also write like r sine of theta is phi, because the height is common for these two triangles. These two right triangles are there. For these two right angle triangles, the height is common. So I can write it like this. So sine of phi can be written as r by l times sine of theta. Okay. Um, my screen share got ended. I'll share again. Okay, just give me a minute. Yeah. So I can say sine of phi is equal to r by l sine of theta. So basically I can convert phi into theta. Okay. And then you can differentiate this s to get the velocity and acceleration. Okay. Differentiation of s with respect to uh, uh, theta you can do, and you can get the velocity and acceleration. Okay. So this is what you can get ultimately, the relationships for the displacement, velocity and acceleration. Okay. Now the main question here is how we can do the force analysis in this slider crank chain, okay, or slider crank mechanism. Okay, we can use from geometry, we can directly calculate s, we can differentiate s and get the values of velocity and acceleration. It's straightforward. Force analysis is little complicated because we have to calculate the force, like what is the force exerted on the piston, okay, um, what is the force on the crank, and basically what is the turning moment ultimately we get because of that frictional, because of that piston force. Okay, so imagine an IC engine. In IC engine, what do you have? You have let's say suction stroke, then compression stroke, and then power stroke you will get. Okay, so basically assume the expansion stroke where you have some um, combustion of the fuel and um, air. Okay, and what will happen is in that case some force is exerted on the piston. Okay, um, let's say area of the piston is a, and on that area some force is applied, so it will create some pressure, and um, ultimately that pressure makes the piston to move in the downward direction, and we call it as a power stroke. So yeah, so it looks like something like this. Okay, so this is our piston. Draw this figure. Let's assume like this is our piston, shaded portion. Okay, this is our piston. Now, assume that let's say um, some pressure is acting on this piston. Let's call this as let's call it as a P. Okay, let some pressure is acting on the piston um, because of uh, the combustion of the fuel and air. So piston will try to move in downward direction. So reaction force to that will be F2 times A2, okay, which is exerted by the piston. And the piston is connected by connecting rod. So if I draw a free body diagram, something like this, okay. So this FP, you can say it as a piston effort, okay. And basically to the piston we are directly connecting the connecting rod, okay, which might be at certain angle at that particular location. So we have to use a generalized term, f rod at angle phi can be 0, phi can be 90, okay, it is varying. So if you look into these two diagrams and write down the net force acting on the piston, which is called as a piston effort, um, will look like this. Fp is equal to Fg minus Ma. Okay. So this pressure is like this pressure will be creating Fg force. Okay, let's call this force as Fg. Okay, let's call force coming because of this gases is Fg. Okay, the pressure P and the corresponding force will be Fg. So Fg, I'm saying it as a force due to the gases, which is in one direction. Inertia force is in opposite direction. So total or net force on the piston will be Fp, and it is given by this relation. Okay. Now this Fp, we know we have to transfer it to connecting rod, we have to transfer it to the crankshaft, and we have to transfer it to the turning moment at the crank. Okay, because ultimately force we are getting from the gases itself, and the same is transferred to the piston, connecting rod, and then crank, and the basically your it will create a turning moment, correct. So rotate in case of IC engine, reciprocating motion of the piston is converted into the turning moment, which is a rotary which will create a rotating motion of the wheels. Okay, so now now if I let me just go to the next slide, but before that you should know this, um, how much, let's say Fp is the net force acting on the piston, then F rod or the load taken by the connecting rod will be Fp by cos of phi, because horizontal component of this force is F rod cos of phi, that is force in the connecting rod into cos of phi is equal to Fp. We know if you do the sum of all horizontal forces equal to 0, and from this we will get the F rod equal to Fp cos of phi. Okay, Fp divided by cos of phi. Whenever phi is 0 degree, cos 0 is 1. So basically we will say that piston and connecting rod are in the same line, and ultimately whatever force is or whatever net force is on the piston, same force will be taken by the connecting rod. But if it is making some angle, in that case, and the force which is applied on the connecting rod, or force which is taken by the connecting rod, is less compared to that of um, what the piston is getting. Okay, so that is what we can understand from this. Is it clear till this? Any doubt? Can I proceed to the next slide? Now let's try to understand the, so we have just understood the connection between connecting rod and piston. Now we have to understand the connection between connecting rod and crank. Okay, so look at this figure. This is our connecting rod and this is our crank. Okay, so yeah, so this is our, let's say, F rod. Okay, F rod will be the along the along the, let's say, connecting rod, and theta plus phi is the angle in between this F rod and the crank. So I can say that there will be two components of this F rod which will generate. Those are Ft and Fr. Do you agree? That is, can I write Ft is equal to F rod sine of theta plus phi, and Fr, that is radial force, will be F rod sine of theta plus, sorry, cos of theta plus phi. So these are the radial and tangential forces that will be acting on the crank. Is it clear till this? Yeah. So that is what I have. Yes,
Hello, sir.
yes, yes.
In the previous slide, I had it out.
Okay.
The will the minimum force acting on, can we say that FP will be the minimum force acting on the connecting rod? Already F rod is acting at an angle, so at any point cos phi will be greater, less than 1. So F rod will be always greater than FP. It will be only equal to FP at 0. So can
Yeah,
I
yeah, yeah.
assume that my
Yes, yes.
that's correct now?
Yeah, yeah. Understood your point. That cos theta will be 1 only at 0 degree, but
So
at all other
the road will have
locations.
minimum for that.
Yes, yes. Yeah. So only
Okay.
when theta is equal to 0 degree. Hello. Yeah. Only when theta is equal to 0 degree, we can say that the piston force is equal to the force in the connecting rod, and at all the other locations we can see that theta will be less, cos of theta will be different, so it will have some value which is less than 1, and then at that point you can say the F rod will be the maximum. So minimum value is correct, minimum value is FP, you can say. Yeah. Now coming towards this um, connection between connecting rod and crank, I hope you understood till this Ft and Fr, how they are calculated. So F rod we have already described. We have written F rod in terms of Fp. So F rod is Fp by cos of alpha. So I can say that tangential force acting at the connection between the um, connecting rod and crank will be Fp by cos of phi into sine of theta plus phi. So I'm just using this equation 1, and in this I'm putting the value of F rod from the previous slide. So we can clearly see here F rod is equal to Fp by cos of phi. That is what I have kept here. Okay, so we have written how much force exerted, uh, like how much force the crank can feel, tangential force, if F the force faced by the piston, and this Ft is a tangential force and it will create a turning moment. So can I write now turning moment at, let's say this point is O. Okay, let's say this point is O. Turning moment about the center of rotation of a crank will be equal to this F this ft into the r. Can I write it like this? Turning moment is equal to ft into r. Yeah, because this is our crank, this is our crankshaft, and this is our ft. This is our crank, which is of a distance or which is of a length r. So I can say turning moment is equal to ft into r, and we already calculated ft, which is fpy cos of phi into sine of theta plus phi. So this is very important relationship. You don't have to do this derivation in exam, but you should know the formula, because there is a chance that you can expect a question like they will give some um question like a piston force, net force on the piston is this much, then what will be the turning moment uh, uh, at the crank? So you should be able to calculate it using this relationship. Okay, so the major type of question from this uh, um, chapter is mainly is only this. Okay, there is they can ask question only from this topic of slider crank mechanism they'll give, and they'll ask you to find out the forces either in the crank, either or the connecting rod, okay, or the turning moment at the crankshaft. So this is what you can expect from this chapter. But we have one more topic here in the same chapter, that is dynamically equivalent link, and that is also very important one, which we'll study now. Can I proceed to the next slide? You can expect a theoretical question from that topic. What is like what are the criterias we have for a dynamically equivalent link and all? Okay, so write down heading dynamically equivalent link. Okay, dynamically equivalent link. Okay, now generally whatever masses which we see, or whatever real or whatever real time links we see, like a connecting rod or a crank, all these are with a distributed mass system, right? So we don't have like a connecting rod in which mass is only at the center and at rest of the places we don't have mass. All practical application links are with a distributive mass system. But problem is, you know that like in mechanics also you might have studied, like if we have a um, uniformly distributed load or uniformly varying load, the problem is a bit difficult to solve compared to the point load condition. And uniformly distributed and uniformly varying load are also the special situations, like, but there can be there can be a like very distribution a distribution of mass which you cannot like just simply convert like a uniformly distributed or uniformly varying. It can be non-uniformly distributed, non-uniformly varying as well, right? So it becomes complicated to analyze that system of a distributive mass, and to make the calculation simpler and perform the dynamic analysis, we can convert that dynamically equivalent link. We can convert that distributive mass system into um, a system of masses, okay, which I have shown below. Okay, so this is the figure number 1, you can say, and this is figure number 2. In figure number 2, you can say a system of masses is there, which is like dynamically, which we assume that like um, I can uh, draw this distributive mass system into the figure number 2 as I have shown, but I can say that this is dynamically equivalent link only under certain situation. Okay, it has to follow some rules, then only we can say like I can use figure number 2 and say at figure number 2 is equivalent to figure number 1. Why? Because uh, it is satisfying certain criterias. Okay, it is satisfying some dynamic conditions. Then only I will say that the figure number 2 is dynamically equivalent to the figure number 1. Okay, so this is the main intention of creating dynamic equivalent link, that solving a distributive mass system is complicated, and converting it into the system of masses makes it simpler. But if we are converting the system of masses, we have to make sure that we are generating, or we are drawing a dynamically equivalent link. And the link which we have drawn with the system of masses is a dynamically equivalent link only if it satisfies the three conditions. Okay, the three conditions are here, like m1 plus m2 is equal to m. It means total mass of the link will be equal to sum of the masses. Sum of the masses will be equal to the uh, sum of the masses equal to the total mass of the link. So mass should remain same. That is first criteria. Second criteria is m1 l1 equal to m2 l2. Okay, the meaning of this is center of your CG should not change. Whatever moment the mass is generating, m1 mass is generating and m2 mass is generating, about CG before and after should remain same, right? So ultimately what is the meaning of this is your CG, center of uh, gravity, should not change. And third is your moment, uh, is, you can say that I is same. Okay, total moment of inertia will not change. Okay, total moment of inertia will not change. And how they are like calculated, I will just show you simply, or how they are decided. uh, I'll just show you through some simple tricks. Okay, so the first point, we are saying mass should not change. So assume, let's draw this simple figure here. I have drawn already. You can just have a look. So I am drawing this link which is having mass m and I is the moment of inertia. And our system is having some force F, which is applied at a distance r cg. Okay, and because of this force, body is moving with certain acceleration. So force is equal to mass times acceleration, we can say, is the inertia force. So acceleration remains same. Okay, whenever I am saying equivalent link, if original link is moving with certain acceleration, our equivalent, dynamically equivalent link should also move with the same acceleration, right? That is the base criteria. And then assuming that acceleration is same, I can say F by m is equal to F by m1 plus m2. We cannot change the external condition. External force F is same. So I can say that m1 plus m2 has to be equal to the m. So this is how same mass condition is derived. Okay, same mass condition is derived from the uh, same acceleration, because it's a dynamically equivalent link. So whatever dynamic um, effects our original system is feeling, the DEL, dynamically equivalent link, should also feel the same. Second one is angular acceleration should remain same. You know, this force will create a moment of F times R, F into R, in one direction. So I alpha will be the inertia force in the opposite direction. Okay, so Fr is a clockwise, for example, then I alpha will be counterclockwise. So I alpha is equal to Fr, we can say, as I already written here. So from this I can say alpha is equal to Fr by I, Fr by I. Okay, external force we are not changing. Do I agree? External force we are not changing. It means I is also same. Okay, the only thing basically here what we can say is F is external thing, we cannot change. So in order to have the, so this alpha has to be equal to the new alpha which we are getting from the dynamically equivalent link. Okay, and this is possible only when you maintain the same center of mass. Okay, I'll repeat. So basically So this link you are converting into this dynamical equivalent link. In this link also, you will see that your CG will, the force will act at a distance r from the CG. Okay, so your CG location should not change. Your center of mass should not change. Then only you will achieve the same angular relation alpha. Okay, so that's why m1 plus or m1 in times L1 equal to m2 times L2. What is this L1 distance? This is the L1 distance, and this is the L2 distance. And the third condition, what we have studied is, or what we understood in the beginning is, total moment of inertia will not change. Okay, so let's say initially your body is there with a mass m, and radius of gyration is k, for example. So mk square is the um, moment of inertia. Now that has to be equal to the m1 l1 square plus m2 l2 square. Okay, so these are the three criteria it has to follow. Then only you can say that the link the link with a system of masses is dynamically equivalent link to the link with the distributed masses. Okay, so this is just for simplification. You can expect the theory question from this, like which are all criteria to be satisfied for DL and all. So you should know this theoretical background behind it. Okay, mainly if you see the previous year papers, they are asking question from this topic mainly on the slider crank mechanism. Okay, because there you can expect both combination of both sliding and turning pair. So um, it makes a quite tricky problem, and they will they may ask it from that. Okay, so whatever we have studied before, like how piston, how the force exerted on the piston can be calculated, how the force exerted on the connecting rod, crank, and the crankshaft is calculated, turning moment on the crankshaft is calculated, is very important from this chapter. Okay, do you have any doubt in this? Okay, I'll open another presentation here. Okay, um, so this is the last topic of our syllabus, that is balancing of reciprocating and rotary masses. Okay, so in day-to-day life we have like faced this issue a lot. Okay, for example, let's say you have, let's say you have some wheel. Okay, maybe take a simple example of a fan. Okay, in fan, let's say it's a three-bladed fan, and in one of the blade you let's say make it little um, heavier than other two, and if you run the fan, you will clearly see that you'll feel the discomfort, like in terms of noise or in terms of performance of the fan, right? And um, it is not running as per our expectation. Okay, so this is kind of an unbalance we feel whenever a fan will rotate if all three blades are not properly are of different, you can say, weights. So it's not only in rotating component but also in reciprocating machineries also you can see the issues in balancing. For example, um, let's take an example of piston cylinder arrangement, which is IC engine. Okay, in IC engine also uh, you can feel or the unbalanced forces, or we can get the unbalanced forces in this reciprocating machinery. Okay, so in general, I would say that it's not a problem with only uh, rotary machines. We can get the unbalanced forces in reciprocating machines as well. Okay, so it's a reciproc. So that's why the name of the chapter is um, or name of the topic in our syllabus is balancing of reciprocating and rotary masses. So our focus will be only on these points, like if masses are rotating and if masses are uh, reciprocating, how we find the unbalanced force and how can we balance it. So what is balancing? Is the process of designing or modifying the machinery. Write down definition. Process of designing or modifying a machinery so that the unbalance is or unbalanced force, the unbalanced force is reduced to an acceptable level. Okay, and if possible is eliminated completely. Okay, so this is what the definition of balancing. Look at the figure number A here, which I have shown. We have particle of mass m moving in a circular path. So you can see that if it is moving in a circular path, a centripetal acceleration will be experienced by this mass, and force required to produce it, um, the balancing force for this will be mr omega square, which is acting in the outward direction of the rotation. Okay, so and we call it a centrifugal force mr omega square. So what is happening here? The magnitude of this mr omega square will change whenever we have a different value of omega, right? So now we know this concept. Try to implement this concept in a real-time example. Okay, we have a revolving rotor, and in this revolving rotor, this is the axis of the revolving rotor. Okay, and we have some unbalanced mass m here. Okay, so if you don't have unbalanced mass, uh, like every element or every element of the um, or let's say this rotor, if mass is equally distributed, then you will see that there is no any unbalance here. But if let's say uh, or in other words, cg of this rotor, okay, cg of this disk and cg of or let's say cg of this disk is lying on the axis of rotation. I'm talking about the figure number B. cg is on axis of disk or axis of shaft. So we can clearly see it's um, a balanced rotor, I would say, because mass is equally distributed in all the direction. That's why the CG, center of gravity, is along the axis of the shaft. But if CG is at some eccentricity is given by E. If it is at a certain distance from the axis of the shaft, what will happen? As we know, this concept we can apply here. It will generate a me omega square centrifugal force. Okay, so I'm not sure whether you have studied vibrations or not, but if you are not, then you will be going to study there in that it may cause whirling of the shafts. Okay, so whenever we have certain mass, M, which is at eccentricity E, and that is rotating. And because of that, what will happen is shaft will whirl. Okay, and because of this unbalanced 4 me omega square, which is acting away from the center of the rotation. Okay, so this is very common problem in, let's say, steam turbines, or centrifugal pumps and all. So you have to make sure that your CG of the rotor is always lying on the axis of the shaft. Okay, let's take another example, maybe a simple example I would give you. Um, okay, this let's have understand this as a wind turbine. Okay, so a wind turbine, um, let's say this is 10 ton, and I'll make this as a 12-ton blade. So if one of the blade of this wind turbine is quite heavier than the other two, and if this is rotating, obviously we can see that this rotor will feel unbalanced force. Okay, so for example, if it whenever it is coming down, it will get a nodding action, and in the downward direction. And when this basically for each rotation, you will realize that our rotor is unbalanced, and it is causing lot of loading in the other parts of the system. Like this rotor is connected to the main bearing, so main bearing loads on the main bearing will increase, and ultimately it will cause the damage to the main the main shaft and all. So all the other components which are linked to this will kill. So that is why it's very important to balance the system, and to make sure that center of rotation, or let's say CG of this rotor, is exactly along the CG of the rotation. Okay, otherwise we can come across some serious problems. So not only it is causing the impact, or let's say vibratory motion, causing high noise and fatigue, but it's like a human discomfort also because of this noise. And also the machine's performance will reduce, structural integrity and machine foundation, it will get also affected. Okay, so basically this balancing is very important in all the rotary and reciprocating machines. So let's start understanding this topic in more detail. What is static balancing and what is dynamic balancing? Write down heading static balancing. Write down heading static balancing. A system of rotating masses is said to be in static balance if the combined mass center of the system lies on the axis of rotation. Okay, a system of rotating masses is said to be in the state of it's said to be in a static balance. Okay, if the combined mass center of the system lies on the axis of the rotation. Okay. What is the meaning of it? So you can clearly see here, this is the axis of rotation. I'll use red pen. Okay, this is the axis of rotation, and in the in the in this figure 14.2a, you can see um, we have a rotor, okay, with which is solving it with a constant angular velocity omega. Okay, and the number of masses are, say here, 3, m1, m2, and m3. Yes, correct, Sean. That moment about the point of rotation should be 0. Fine. Okay. So all three masses m1, m2, and m3 are at the eccentricity of r1, r2, and r3 from the center of rotation. So what is the vector sum of all the forces? So you know that mr omega square, um, it will have let's say the force in this direction and all this direction. So ultimately vector sum of all the forces will be mr omega square, okay, plus, or no, moments, Sean, no, moments is wrong word, okay, because it's not, um, we can clearly see here, this is a coplanar concurrent force system, and whenever the force system is concurrent, means all the forces are passing through same point, then it will not create moment. So summation of all moments is equal to 0. This is your equation of equilibrium. You cannot apply in this case because none of the force will create the moment about the point here, because all the
Uh,
forces are
Hello, sir.
yes.
Like when it is static balancing, we are not protected enough. Like I thought, like we are with the weight of the books. Like it is not like that.
Okay,
Like
okay.
I
So
thought that
okay, so you might have like assumed this kind of system maybe, and about this axis, um, or you might have understood it as a different plane, but this is a same plane. Um, try to understand this situation. M3 R3 M R3 omega mr omega square. Sorry, R2. Yeah. So basically, these M1 R1 or M1 M2 and M3, these are the three masses which is at eccentricity R1, R2, and R3 are in the same plane. So mr omega 1 square is the centrifugal force for the first mass. For the second mass, M2 R2, M2 R2 omega square, and for third mass, M3 R3 omega square are the centrifugal forces. If sum of all the centrifugal forces is 0, M1 M1 um, M1 R1 omega square plus M2 R2 omega square plus M3 R3 omega square. If it is 0, then we'll say that this rotor is already balanced. Okay, are you following it? So this is a rigid rotor, for example, revolving with a constant angular velocity omega, and the number of masses are 3, uh, and sum of all the centrifugal forces we are getting is 0, means this rotor is already balanced. But what if this sum of all the forces is not equal to 0? Then it is unbalanced. It is unbalanced rotor, and to make it a balanced, what we have to do is we have to attach a counter mass mc. Okay, so I'll use a red pen here to highlight. This is mc, which is at rc distance is um, connected, and now the new relation is plus you will get MC RC omega square, and then now it is equal to 0, and this will be a balance, this will create a balance in the system. Are you following it? Yeah, so basically previously 3 masses were there and they are not, the centrifugal force of them is not balancing each other. Then we are putting one more mass, which is counter mass MC, which is at a radius RC um, from the center, okay, of the rotor, and now that is helping us to make the balance the rotor basically. Okay, yeah. So omega is same in all this uh, terms. I can directly write now MCRC, or basically M1R1 is equal to M1R1 plus M2R2 is equal to plus M3R3 is equal to 0 if it is the balance case. If it is not balanced and we are making it balanced by using MCRC, I can write it as M1R1 plus M2R2 plus M3R3. It is not equal to 0, unbalanced we can say, and we are making it balanced by using MCRC and then equal to 0. Okay, so we are converting an unbalanced into balanced rotor by adding MCRC. Okay, so now this I can write it as summation of all the MR, summation of all the masses and the radius, plus summation plus mass of the counter mass and the counter radius for it equal to 0. Okay, can I write it like this? So how the system will look like in reality? In mechanics you might have studied, this was our first mass. So can I write it as M1R1 omega 1 square, M2R2 omega square, and this is, let's say, M3R3 omega square, and this is our counter mass, which is creating a moment MCRC omega square. So this kind of figure I can draw. These are the coplanar concurrent force system. Let's say this is at angle theta 1, this is at angle theta 2, and this is at angle theta 3, and the last one is at a theta c. Okay, this angle is theta c. So can I write, if I take a horizontal component of each force and can I equate it to the horizontal component of this balancing force, or the counter uh, or the horizontal component of this centrifugal force generated because of this counter mass? Yes, right. So I can basically write it as summation of mr cos of theta equal to, plus mcrc plus mcrc cos of theta c, cos of theta c equal to 0. Are you getting how I have written this? I have done the summation of all horizontal forces equal to 0. That's all. Can I also write summation of all vertical forces is 0, mr sine of theta plus mcrc sine of theta c equal to 0. I can write it like this, right? So from this first relation, I can further write it as mcrc cos of theta c is equal to minus summation of mr cos of theta. From the second relation I can write mcrc sine of theta c is equal to minus summation mr sine of theta. Okay, so ultimately if you just square these terms first, okay, and add them, sin square plus theta plus cos square theta will become 1, and ultimately you will get mcrc will be equal to mcrc will be equal to under root of um, summation of mr cos of theta whole square, because minus minus will become minus a square is minus 1 a square is 1, so I have neglected it already, plus summation of mr sine of theta whole square. Are you following it? This is how I can calculate the mcrc. Okay, so decide them up, and accordingly you can decide the mass and r distance, and just balance the unbalanced rotor. Is it clear till this? Any doubt? And now the only point is how to find the theta c. If I divide these two equations, mcrc will get cancelled, mcrc will get cancelled. Sine of theta divided by cos of theta is tan of theta. So I can write tan of theta c minus minus will get cancelled. Summation mr sine of theta divided by summation mr cos of theta. Okay, so that's how I will calculate the tan of theta c. Is it clear? So in this way you will be able to calculate the mass of this counterweight, rc of the counterweight, and the theta c of the counterweight. So these are the three things which are very important to balance the system. Okay, so that's how we can make the system of rotating masses having center of the system lies on the axis, or CG of the system, we can say, we can make or the basically the center of the system we can make same as that of axis of rotation. So that is the static balancing. Combined mass center we are making equal to the, or making sure it is lying on the axis of rotation. So that's how we can make it sure, because we are considering it as a coplanar concurrent force system. So this is a coplanar non-concurrent force system. In mechanics you might have studied this coplanar non-concurrent force system. Non-concurrent force system. So here you can say the moment part come into the picture. So whenever the force system is coplanar non-concurrent force system, apart from summation of all the forces, you have to use one more relationship. Summation of all moment has to be equal to 0 for the equilibrium. Okay, so this you can Sean, you can implement in case of non-concurrent force system, and here the term dynamic balancing comes into the picture. Okay, so for example, here m1 r1 omega 1 square and m2 r2 omega 2 square, for example, is same. It means that it is already a balanced system. Do you agree? It is, this entire system is there. Okay, on the shaft we have a mass m here, we have another mass m here, and the shaft is rotating like this. So centrifugal force from this will be in this direction, centrifugal force by this will be in this direction. Sum of the all vertical forces is same. So if m1 r1 omega square equal to m2 r2 omega square, means it's already balanced. Okay, and we have studied if it is not balanced, how to make it balance in the last slide. But now, as they are not non-concurrent, it means there is some distance between them. Okay, both the masses are at a distance L from each other, which I have shown in this figure. So whenever this several masses rotate in different plane, not only the centrifugal forces comes into the picture, but centrifugal couples will also come into the picture. So do you know what is couple? Whenever we have two forces, uh, equal and opposite forces separated by some distance L, it will form a couple. Couple means a moment, basically. It will create a moment. And the value of this will be, let's say, F is the force value and L is the distance between them. Then the couple will be F into L. Correct? In mechanics, you might have studied this. So, but till whatever you have studied, we were able to balance out the centrifugal force, but we are not able to balance this F into L. What is this F into L? F into L is the couple. Yeah. So basically, the system is of the rotating masses is in dynamic balance. So whenever we are saying a dynamic balancing, it means not only just balancing the centrifugal forces, but also the couple. So write down dynamic balancing. Write down dynamic balancing. A system of rotating masses are in dynamic balance or is in dynamic balance. System of rotating masses is in dynamic balance. Okay, when there does not exist any resultant centrifugal force. Okay, when there does not exist any resultant centrifugal force as well as resultant couple. Okay, so this is very important. Resultant centrifugal force we have already studied, and the resultant couple also we are bringing here. Okay, so basically it's always mm, uh, or we can say if system is non-concurrent, then there is always chance of a couple will generate and to uh, basically counter this torque or counter this couple in order to balance it, not only from the load's point of view but also from the moment's point of view as well. Okay, so what you can do is here you have to generate a counter couple. Okay, and that counter couple will help you to um, balance it. So what is the value of counter couple? I will I'll go to the next slide. So you can clearly see here m1 r1 l omega square plus m2 r2 l omega square, both are same in this case. Okay, um, because or this is same basically m1 r1 omega square plus m2 r2 omega square, but l is the distance between them. So I would say m1 r1 l omega square will be your m1 r1 omega square into L is, let's say, your unbalanced couple or the resultant couple. And in order to balance it, you have to, let's say, forget about omega, because you will, whatever mass you will put, that will also have the same omega. Uh, so I will rub this part, okay, and I can say that it has to be equal to the m mc rc lc. Okay, mc rc lc. I hope you are following this. Um, M1R1L will be equal to now MCRCC. So what we are bringing here, we are bringing now, let's say, not only just the counter mass and at a particular length, at a particular let's say distance from the center of rotation, but also at a particular length uh, to form a couple. Okay, so this is how. So if they ask you what is the resultant couple, or what should be the balancing couple, then the value is MCRCLC, and that is equal to the total resultant couple of an unbalanced system. Okay. Yeah.
Hello, sir.
Yes.
How will we draw this in that diagram? Like NC, RC, NC. Like, will there be two NC? Like,
Uh,
uh,
will there
like
be?
yeah, while in that previous diagram, we have to generate a couple, right? So to balance this, we will be adding two counter masses in this figure. We'll be
Yes.
adding two
Yes.
MC or like just
Yeah.
one M. Okay.
Yeah. Yeah. We add two. Ultimately, we have to add the two counter masses, but MC1, you can say um, MC1, okay, which is at a distance RC1, okay, and similarly MC2, which is at a distance RC2, okay, and the distance between these two masses, let's say, is LC, okay. Um, so ultimately, what we are making is whatever resultant. Um, okay, I'll go to the previous figure. So in this figure itself, let's say if I draw to make, sorry, my screen stopped. Just give me a minute. I will. Okay. So whatever I have written is gone. Okay, I'll rewrite it. So try to understand what I was saying. So here, if I put one mass, okay, let's say it is MC1, and let's say here MC2. This are distance RC1 and RC2. So here, what kind of couple I would expect? I would expect a counterclockwise couple. Do you agree? And the value of this counterclockwise couple will be MC1 R1. Okay, MC1 into R1 into L omega square. Sorry, or MC1 R1 omega square into L is equal to, this is basically that couple, and we know either it will be equal to this or MC2 R2 omega square into LC. Let's call it as LC. Okay, LC, right? Because the distance between them is, for example, LC. So uh, here omega omega is cancelled. You can just neglect it. So MC1 R1 LC equal to MC2 R2 LC. So here, first one is static balancing, which means this one M1. So here this force is in upward direction, this force is in upward direction, and these two forces are in downward direction. So first of all, we have M1 R1 omega square plus MC2 R2 omega square plus RC2, sorry, and plus M2 R2 omega square, which is in downward direction. So maybe, or let's write equal to, plus MC1 RC1 omega square. So omega square, if you cancel out from all the terms, This is the requirement of the static balancing, and this is the requirement of dynamic and balancing. So in other words, the simple expression for this will be summation of all the existing MR should be equal to or plus MC1 R1 plus MC2 R2 equal to 0. Is it clear now? This is for static balancing. And for dynamic balancing, as I said, not only just M into R, you have to also consider this uh, consider the distance between those two counter masses. So you are correct that in this case you have to use the two masses because we have to generate a counter couple. Couple will generate only when we have two forces, okay, and which are in opposite direction and at a certain distance from each other. So that's why that um, we are using two masses here. Okay, so that two centrifugal forces will generate and they'll be in opposite direction and separated by certain distance, so we can form a counter couple. Okay, so I can, in general, I can write, so this is for just two masses. So if we have more number of masses, in general I can write summation of M R L plus um, uh, just a minute. Yeah, summation of MRL plus this uh, yeah couple like MC. Either you can take two or one. Let's say you are taking two, MC2 R2 and LC. Okay, this is has to be 0. Try to understand here. Here you are not doing sum of all, so that is why I am not adding two MC1 RC1 because it's a couple forms by two forces. That's why only one single term I'm using here. Okay, and here also you will not have let's say if 8 forces are there, then there is chance of 4 couples, so only 4 terms will come, and then this will be the fifth balancing term. Okay, so this is how you can do the not only the force balancing but also the moment balancing or the couple balancing. Okay, clear? Same approach, just um, here we are using in static balancing we are just balancing the centrifugal forces. In dynamic balancing we are balancing out the couple as well. Okay, so this is all about the rotating masses. Okay, so it's for rotating masses it's quite simple, and most of the time I expect that they will ask you, though, if they are asking from this chapter, ideally there are very less questions. If you see previous year papers from this chapter, um, even if they ask, like, mainly they will ask it from the rotating masses itself. So with this knowledge you should be able to solve it. Another point, but still we have in syllabus, we'll study that, that is balancing of reciprocating masses. Balancing of reciprocating masses. Okay. Balancing of reciprocating masses. If you remember, in the previous chapter, dynamic analysis, I have given you the formula for the displacement, yes, and basically then how we'll calculate the velocity and the acceleration. Okay, so how the acceleration was looking, the acceleration, as I mentioned before, is denoted by F, and that is equal to r omega square cos of theta plus cos of 2 theta divided by n. Okay, and where n is equal to L by R. Okay, let me just show you that slide so you can correlate. Yeah, here this is the S. Okay, and mr omega square, sorry, here write down this as mr a is equal to alpha, that is acceleration is equal to mr omega r omega square, sorry, cos of theta plus cos of 2 theta divided by n, where n is equal to L by R ratio. Okay, so same formula I am using here now. Okay, same formula I am using here. Now this is our acceleration, and what is the um, force because of the acceleration? Capital F is equal to mass times acceleration, that is ma, and I can write it as mr omega square cos of theta plus cos of 2 theta divided by n. So it is mr omega square cos of theta plus mr omega square cos of 2 theta by n. Correct? We can write it like this by splitting this bracket into two parts, and so this part is called as a primary accelerating force, and this part is called as secondary accelerating force. Okay, and what was the value of n? If you remember, n is equal to L by R. So the n value is always greater than 1 because our connecting rod is larger than or longer than the crank. So the secondary term is always like a smaller. This term, secondary acceleration term, is more or less, let's say, small compared to the primary uh, force, and you can safely neglect it for the engines which are rotating with a slow speed. So this is why the more important is uh, the primary accelerating force. Okay, so try to understand the situation here. We have a piston which is moving, and inertia force will be this. Inertia force will be the same, mr omega square. Okay, look at the figure. If this I'm talking about the figure number A here, crank is rotating in counterclockwise direction, it will move the piston towards left hand direction, so the inertia force will be in the right hand side direction, that is omega mr omega square cos of theta, which is an unbalanced force now. Okay, and we have to balance this. Is it clear till this? What is the unbalanced force in case of reciprocating masses? How it is calculated? Yeah, okay, I'll repeat. We have calculated the displacement. Okay, I'll just go to the next slide. If you remember, this was our piston, this is our R, this is our L, and this is a theta, and this is phi. We have calculated some S. Okay, S is equal to R cos of theta and L cos of phi, and we have differentiated this to get the velocity and acceleration. And acceleration of the and we have got this relation for the acceleration, that is r omega square cos of theta plus cos of 2 theta by n. So we know that our piston is moving with this acceleration. Okay, so if focus on the figure number here, if crank is rotating in counterclockwise direction, our piston will move in the leftward direction, right? So what is the inertia force on the piston, which is unbalanced force? It's not in equilibrium, so it's unbalanced force in the rightward direction, which is opposite to the motion, that is mr omega square cos of theta, right? Because force is equal to mass times acceleration, and mass we know m is the mass of the piston, and alpha acceleration is this value. Okay, mass times acceleration. Sorry, and we already know acceleration of slider is r omega square cos of theta plus cos of 2 theta by n, and we already studied that the secondary acceleration can be neglected, so only the mr omega square cos of theta is the we can say is the force, inertia force on the rotate sliding member, which is piston in this case. Is it clear now? Mr omega square cos of theta. So I'll just use this red pen to highlight these things so that you can. It's just mass times acceleration only. Okay. But acceleration we are split it into two parts, and we have taken only primary part of it, because in secondary part the value of n is larger than 1, so the secondary part becomes smaller and can be neglected. Okay, now the next point, look at the figure number B here. In figure number A, what I have shown is the inertia force and the accelerating force. But in the figure number B, what we are trying to understand is forces acting on the engine frame due to this inertia force. What is meaning of engine frame? Engine frame consists of this your crankshaft bearing, okay, and this guide wheels, okay. So I'm using red pen to highlight it, the engine frame. The engine frame consists of this, the main bearing on which uh, you are rotating the crank, okay, or basically the crank pin and uh, the guide wheels, okay. So on these two parts, what are all the forces are exerted by the inertia force? Okay, one is the normal reaction, that is F41 at this location at the piston, okay, because the piston is in contact with the surface or the guide ways, so you will have a normal reaction. And we can clearly see this F21 here, okay. So basically we have some component of force, so where basically this is a hinged support. In support we'll have two reactions, one is a vertical reaction, another is a horizontal reaction, okay, because our crank can freely rotate, so it is a hinge support. So at this point we have two reactions, one is vertical and horizontal. So F21 vertical and F21 horizontal, these are the two reactions, and here we have F41 vertical. So these are the three different forces that are exerted by this inertia force on the engine frame. Do you agree till this? Is it clear? Are you getting like how we have written this? Yeah. Now, out of this, which are all the unbalancing force? So in horizontal direction, how many forces are there? Only one force is there. What is the value? F21H. Do you agree? This is the only force in the horizontal direction, and we don't have any other force in the horizontal direction to balance it out. Okay. So F21H, you can say it as a unbalanced shaking force, which will try to, let's say, unbalance the reciprocating motion of the slider. Okay, so write down F21H is the unbalanced shaking force. Whereas F21 vertical here and F41 vertical, they are like opposite to each other. They will balance out each other. Are you following? So F41 and F21V, they are like in opposite direction to each other. One is acting downward and this is acting upward. So they will balance out each other. But you can clearly see they are at the different locations. They are not concurrent forces. So it will generate a couple. Do you agree? So there are two kind of issues in our system we are facing because of this inertia force. One is F21H, which is a shaking force, and a couple, which is, you can say, coming from this F21V and F1, we can call it as a shaking couple. So I would say uh, shaking force F21 horizontal and shaking couple, which is forming because we have F41 in upward direction and F21 vertical in downward direction. They are basically same, balance out each other, but they are at a certain distance s from each other, and it is generating a counterclockwise couple. Okay, but out of this, whether it is causing any issue with the reciprocation, this will just try to tilt the entire system. But if your guideways are and the frame is strong enough, that will be able to sustain it. But we don't have any balancing force for this F21H, right? Do you agree till this? Because in F21H force, we don't have any other force in the left hand side direction. How can we make it balance? Anyone? Can anyone tell me how can we make it balance? So this F21 is unbalanced force, only an unbalanced force in the system, and it may happen the smooth running of the engine. So piston will not um, move smoothly. Even if you make a vertical system, what will happen? Then also you'll face issues. Okay. Uh, Only this, nothing will change even if you make the vertical system. So this F21 vertical will become horizontal and F21 horizontal will become vertical. So ultimately you will end up with a similar situation, but in just opposite direction. We can do this, or we can do the balancing of this mass by using a counter mass. Okay, which is directly opposite to the crank. So look at this figure number C now. In figure number C, what I am doing? Adding a counter mass M exactly opposite to the crank. Omega square will be the centrifugal force of it, and as this angle theta, this also has to be theta, and horizontal component of it is mr omega square cos of theta. Okay, so mr omega square cos of theta will be your horizontal component, and that is actually balancing your primary um, primary force, which is or which is your inertia force, that is balancing it out. Are you following it till this? Look at the figure number C here. We have same reciprocating mechanism here, but a counter mass of M we are attaching at a distance r. Okay, in the, and horizontal component of it is mr omega square cos of theta, as I have shown, and that is in the opposite direction to that of our inertia force. Okay, and it is neutralizing the unbalanced force basically now. But problem with this is it will generate one force in downward direction, that is mr omega square sine of theta, and this will become a new unbalanced force. New unbalanced force. Is it clear till this? Do you understand how we are making a horizontal force balanced, but that is causing a new unbalanced force, that is generating a new unbalanced force? So previously, let's say our system was feeling jerks, unbalance in the let's say to and fro motion of the piston, but now because of this new unbalanced force in a vertical direction, our system or mechanism will feel jerks in the up and down direction. Are you following? So previously what was the situation? The jerk was in horizontal direction, because horizontal direction unbalanced force is there, so the sliding motion was not proper, and now we balanced it with this counter mass, but it is creating a new unbalanced force in a vertical plane, which is causing mechanism tries to jump and up and down, okay, because of it. So ultimately it is very difficult to balance the you can say the reciprocating masses, okay. You can, even if you are let's say balancing in the horizontal direction, vertical direction, some forces are getting generated. So as to minimize the effect of this unbalanced force, we have to do some compromise now, okay. So rather than let's say using this m exactly same as the mass of the slider, you can say, okay, what you have to do is you have to use some let's say some portion of the mass, okay, fraction of the mass you have to use, okay, let's say maybe 2/3 or something. I'll just go to the next slide to explain it. Yeah, so mr omega square cos of theta is our unbalanced force, right? But you can balance it if you can somewhat balance it by using cm is, let's say, a component of mass, okay, you can say, or fraction of mass. C is a fraction, and cm will be the fraction of mass. It can be, let's say, 2/3 of m, it can be half of m, etc. Because we know if I use completely m, um, another new unbalanced force of higher magnitude is getting generated in the vertical direction. So I have to do some compromise now, and I can just use this much balance force, okay. So this is your primary balance force, okay. Your primary unbalanced force will be, now let's say if it is 2/3 of mass you are using, primary unbalanced force, primary in this case is a horizontal force I'm talking about, is 1 minus c times m r omega square cos of theta. Do you agree? These are the if I am not completely avoiding the horizontal force um, by using mass m, but for fraction of mass m, I will not be able to completely eliminate this unbalance. So I'm just balancing this part of this cmr omega square cos of theta part of it. So unbalanced force will still now 1 minus c m omega mr omega square cos of theta. So basically I'm trying to reduce the unbalance in the x direction, okay, by some fraction. And as I said, whenever you are adding some counter mass, it will generate a vertical motion. How much amount of vertical motion it will generate now? cmr omega square sine of, correct? Previously it was mr omega square sine theta, but now I am using the mass of let's say some fraction c, then cmr omega square sine of theta will be the vertical component of the vertical component of the centrifugal force, which will again remain, which will remain unbalanced. Are you following it? So this kind of compromise you have to make in order to uh, basically, if you feel that unbalanced force is high, then you can do a small balancing of it, but with a cost of little unbalancing in the vertical direction. Okay. So what is the resultant unbalanced force? So this is in vertical direction, this is in the horizontal direction. So resultant will be under root of 1 minus c mr omega square cos of theta plus cm r omega square sine of theta whole square, a square plus b square, correct? Horizontal forces square plus vertical forces square, and under root of that you will give you the resultant force. Okay, so if you differentiate this resultant force with respect to c and equate it to 0, you will get c is equal to 1 by 2. Okay, so this is a limiting case. Resultant unbalanced force will be minimum, so this value will be minimum when c is equal to 1 by 2. Okay, but you have to take into the consideration that unbalanced forces in the direction of line of stroke are more dangerous compared to that of perpendicular to the line of stroke. So this is very important line. I'll write here. In reciprocating engine, why we are making that compromise? Because in reciprocating engines, the unbalanced forces in the direction of line of stroke are more dangerous okay, than the forces in the perpendicular to the line of direction, in the perpendicular direction to the line of stroke. Okay, so what are the direction of the line of stroke is our horizontal, right? So the direction of line of stroke means horizontal. And what was our horizontal force? F21H, correct? And perpendicular to the direction of the stroke means vertical. And what was our whatever our forces? F21 vertical, and now the other one is sine component of it. Okay, CMR omega square sine theta. Okay, uh, I hope you understand like um, why we are making this compromise. We are making this compromise because the forces in the horizontal direction are more dangerous compared to the vertical. Okay, so it's along the line of action, whatever forces are there along the direction of line of stroke, whatever forces are there, they are dangerous compared to the um, perpendicular to it. Okay, so that is the reason behind this compromise, and we cannot fully avoid it. If you want to fully avoid it, new unbalanced force will get generated, and that will cause system to jump up and down. Okay, rather than having issues with the to and fro motion. Okay, so we have to do the compromise here. Is it clear till this? Yeah, okay. So that's all you have here for this chapter. One is balancing of reciprocating masses and balancing of rotary masses. We have studied that in balancing of rotary masses, it's a static balancing plus dynamic balancing. Static balancing includes like balancing your forces coming from the centrifugal force, mr omega square. Okay, so only m and r, these are the two parameters, and you have to find and the theta corresponding to it. We have studied how we can calculate it. In case of dynamic balancing, we don't have just force balance, we have moment balance as well. So we have um, since all the masses are rotating at different planes, the force system will be coplanar non-concurrent force system. So there is a chance that couples will generate. So in order to do the dynamic balancing here, you don't have to just balance the forces but also the couples. Okay, and we have studied that how can we do it. Okay, so we have to put two different masses in order to make a counter couple to balance the resultant unbalanced couple. Okay, that is the part of the balancing of rotating masses. In balancing of reciprocating masses, we have studied that the main force which is which is unbalanced force is inertia force. And what is happening because the inertia force on our frames and guideways, we will get a reactions, that is F41, F21 horizontal and vertical. And out of this, F21 horizontal is the only one force which is an unbalanced force. And we have studied if we can balance it out by putting a counter mass, but if you want to fully balance it, it will create a larger new unbalanced force in a vertical direction. So previously our um, mechanism was feeling jerks in to and fro motion. Now it will feel jerks in up and down. Now it will feel jerk in the vertical motion. Okay, so the um, mechanism will tends to move up and down, and that is also not good. So that's why we are making a compromise here to make some to balance out some fraction of the horizontal force in the cost of a new small amount of um, unbalanced force in the vertical direction, because the it is more important to balance the force in the horizontal direction as they are dangerous compared to the vertical forces. Okay, so this is all you should be aware of as far as balancing is concerned. I would expect that mostly you if they're asking questions, they'll ask you from the they will ask from the rotary system only. Okay, so anyways, when we study some problems, these things will get revised in, so you don't have to worry. And still, if you have any doubt till this, you can feel free to ask me. Yeah, Shruti, I'll go back. Actually, what happened is, Shruti, whatever I have written is gone from this PPT, um, because the presentation was slightly was got ended suddenly, and I don't have anything here. Do you have any specific point I can? Okay, which formula you want? Could you please? SVA. Okay, okay, that we already have. Yes, yeah, you can write here. S is equal to r cos theta plus L cos of phi. Velocity is equal to r omega sine of theta plus sine of 2 theta by 2n. And if you differentiate it again, it is r omega square cos of theta plus 2n plus cos of 2 theta by n. Okay. Okay, then if you don't have any other doubt, uh, we'll end our session here, and from the next class onward, we'll start solving the questions. Yes. So we'll start with the um, initial topics like mechanisms and machines and velocity acceleration, and then slowly we will study other topics like gear train, flywheel, governors, gyroscopes, and all. Okay, so next week we'll start our problem solving session. So what we'll do is I would expect you to go through the recording or your notes, whatever you have written, before coming to the class, so that we will together correct all the formulas and concept from that chapter what we have studied. So it will be very easy for us to solve the questions. Okay, directly solving the questions will be difficult. So we will first collect all the formulas and the main points of that chapter, so it will be revision for you as well, and then the problem solving will be quite easy. Okay, so with that, thank you all for joining this class, and let's meet again next week. Thank you.
You are
Bye.
currently the only person in this conference.